Hi, welcome back to Math Review. I'm Yaya Suma. I teach advanced mathematics and programming. In the last topic, we defined what is called limit of a sequence, and we said that a sequence that has a limit is called convergent, and the sequence that does not have a limit is called divergent. Today's topic is about some properties of convergent sequence numbers. Let's get started. Theorem of uniqueness of limit. The limit of any convergent sequence is unique. If a sequence is convergent, then its limit is unique. If we say convergent sequence, it means automatically that it has a unique limit. Any convergent sequence has a limit, and that limit is unique. We can prove this. Proof. Let us give a precise proof by the method of contradiction. Assume that the sequence xn has more than one limit, say two different limits, a and b. That is, limit of xn equals to a when n tends to infinity, and limit of xn equals to b when n tends to infinity, with a not equals to b. There is no harm in assuming that a is greater than b. In the previous lesson, we learned that when we say limit of xn equals to a when n tends to infinity, that means we can choose a small real number epsilon such that we have in the interval a minus epsilon, a plus epsilon, all terms of xn from index capital N up to infinity that are considered very close to a. Epsilon is very small, so is this interval. The same interpretation is true when the limit is b. In order to separate the neighborhoods of a and b, we call this interval the neighborhood of a, neighborhood of b. We let epsilon be equals to a minus b over 2. A minus b is the distance between a and b, from here to here. Epsilon is equal to this distance. Because limits of xn equals to a when n tends to infinity, by definition of a limit, for the given epsilon greater than 0, we have supposed a is greater than b. There exists a positive integer capital N1 such that absolute of xn minus a less than epsilon for all n greater than capital N1. This means negative epsilon less than xn minus a less than epsilon. These two are the same. When we remove the absolute symbol, we get this. We have a minus epsilon less than xn less than a plus epsilon. We can say for all n greater than capital N1, xn greater than a minus epsilon. We consider only this part, equals a minus b over 2. This is epsilon, equals a plus b over 2. Xn is greater than a plus b over 2. Again, since limit of xn equals to b when n tends to infinity, so there exists also a positive integer n2 such that absolute of xn minus b less than epsilon for all n greater than capital N2. That is, b minus epsilon less than xn less than b plus epsilon. We consider only this part. Xn less than b plus a minus b over 2 equals a plus b over 2. If we take capital N equals max of n1 and n2, then when n is greater than capital N, we have n greater than capital N1 and n greater than capital N2. Therefore, we will have both inequalities xn greater than a plus b over 2, xn less than a plus b over 2 for all n greater than capital N. This is impossible. We cannot have xn greater than a plus b over 2 and less than a plus b over 2 at the same time. Hence, we can conclude that the limit of the sequence xn must be unique. You may ask yourself why we choose epsilon to have this value. Suppose we are here, xn greater than a minus epsilon and xn less than b plus epsilon. We want to prove that these are the same value, so that we could say xn cannot be greater than and less than the same value at the same time. A minus epsilon equals to b plus epsilon. By solving this for epsilon, we get epsilon equals to a minus b over 2. We may not know ahead which value to choose for epsilon, but at some point, we need to approximate or to simplify an expression. At that moment, it will be clear which value to choose. For example, prove that this sequence is divergent. Proof. According to the theorem of uniqueness of convergent sequence, a convergent sequence has a unique limit. We know that a sequence that is not convergent is divergent. So to prove that a sequence is divergent, we can try to prove that it is convergent. This means it should have a unique limit. If we find that it is not convergent, then we conclude that it is divergent. Suppose the sequence has a limit a. We write limit of xn equals to a when n tends to infinity. According to the definition of a limit of a sequence, for any positive epsilon, there must exist a corresponding positive integer N, just that this inequality holds for any n greater than N. The terms of this sequence alternate between -1 and 1. As we know, we can choose any small value for epsilon. No matter which value we choose for epsilon, there must always exist a positive integer N, such that this inequality is verified for all n greater than N. Let's choose, for example, epsilon equals to 0.1. This means the absolute of this difference is less than 0.1. This implies the value of xn are in the interval a minus 0.1, a plus 0.1. We can see that even if n indefinitely increases, it is impossible that -1 and 1 be at the same time in this interval. Therefore, this sequence is not convergent, it is divergent. Theorem of boundedness. Any convergent sequence must be bounded. If a sequence xn converges, then the sequence xn must be bounded. A sequence that is not bounded is said to be unbounded. Let's prove this theorem. Suppose the sequence xn is convergent. xn is convergent means it has a limit. Suppose limit of xn equals to a when n tends to infinity. By definition of the limit, for a given epsilon equals to 1, there exists a positive integer N such that absolute of the difference of xn and a less than 1 holds for all n greater than N. Thus, when n greater than N, we have absolute of xn minus absolute of a less than or equals to absolute of xn minus a less than 1. We have absolute of xn less than 1 plus absolute of a. Implies xn is between minus 1 plus absolute of a and 1 plus absolute of a. The inequality absolute of the difference of xn and a less than 1 is true for only the terms that have the indexes greater than N. The index n in this xn is greater than N. So, there are at most n points from x1, x2, up to N which are outside the interval negative 1 plus absolute a, 1 plus absolute a. For the finite number of terms absolute of x1, absolute of x2, up to absolute of N, we can certainly find a maximal one. Hence, the capital M equals max of absolute of x1, absolute of x2, absolute of N, 1 plus absolute of a. Since we have included the value 1 plus absolute of a, then this M is not only greater than all terms from x1 up to N, but also it is greater than all terms which indexes are greater than N. That is to say, for all positive integer, we have absolute of xn less than or equals to N, which means that the sequence xn is bounded. It should be noted that boundedness is only a necessary condition of a convergent sequence. In other words, if a sequence is convergent, then it must be bounded. But a bounded sequence is not necessarily convergent. All convergent sequences are automatically bounded, but the inverse is not always true. Theorem of preservation of sign. If limit of xn equals to a when n tends to infinity, with a different from 0, then there exists a positive integer N such that xn and a have the same sign for all n greater than N. This means if a sequence has a limit a different from 0, then there must exist an index N from which all terms of the sequence have the same sign as the sign of the limit a. If a is positive, then from index N, all terms are positive. If a is negative, then from index N, all terms are negative. Suppose limit of xn equals to a when n tends to infinity and a is positive. According to the definition of limit of sequence numbers, for any epsilon equals to a over 2, there exists a positive integer N when n greater than N, absolute of xn minus a less than a over 2. Again, the choice of epsilon is arbitrary. Absolute of xn minus a less than a over 2 implies xn is between a minus a and half and a plus a and half, implies xn is greater than a minus a over 2 equals a over 2. Since a is positive, this implies xn is greater than 0 for all n. Notion of subsequence. Suppose we have this sequence. Let's take from this sequence the terms, for example, x5, x6, x10, up to xk, so on, and order them in increasing order of their indexes. We call this a subsequence of this sequence. Any infinite number of terms of a sequence xn arranged in increasing order of its subscripts is called a subsequence of the sequence xn, denoted by x sub n sub 1, x sub n sub 2, so on up to x sub n sub k, etc., where n sub 1 less than n sub 2 less than so on less than n sub k less than so on. K expresses the fact that x sub n sub k is the kth term of the subsequence x sub n sub k. N sub k expresses the fact that x sub n sub k is the n sub kth term of the original subsequence xn. Then n sub k is always greater than k. In our example, x5 is the first term of the subsequence. We denote it by x sub 5 sub 1. 5 means fifth term of the original sequence xn, and 1 means first term of the subsequence. X sub 5 sub 1 means the first term of the subsequence from the fifth term of the original sequence. When a term is denoted in the form x sub n sub k, means it is a term of a subsequence. Theorem of aggregation principle. The necessary and sufficient condition that limit of xn equals to a as n tend to infinity is that for any subsequence x sub n sub k of the sequence xn, we have limit of the subsequence when n tends to infinity equal a. If a sequence converges to a, then any of its subsequence also converges and has limit equals to a. In other words, if the limit of a subsequence is equal to a, then the limit of the original sequence is also equal to a. Proof. The correctness of the sufficiencies is obvious because the sequence xn itself is a subsequence of xn. The sequence xn is convergent, implies the subsequence x sub n sub k is also convergent. The necessity is also easily understood. In fact, limit of xn when n tends to infinity equals to a implies that all the terms x sub k are located in an arbitrary small neighborhood of a for k large enough. Since n sub k is greater than k, therefore all the terms of any subsequence x sub n sub k must also be located in this neighborhood. Hence, the limit of the subsequence when n tends to infinity equals a. This theorem will play an important role in the study of limits of functions, which will be introduced in the next topic. This is all for today. I hope you appreciate it. If you like this video, please give it a thumbs up and share with your friends. You can follow me for new videos notifications. Thanks for watching. See you for the next topic. Bye.